Okay, awesome. Many people are interested in databases. So we had a lot of PHP today, but we always miss the part we need to store data somewhere. And there are quite a lot of problems with that. So there was a long introduction, so I'll make it really short. I'm a full stack developer, but I mostly feel comfortable at the back end, mostly with PHP and Laravel. I'm a database educator, which means I do talks like that. I share my learnings, my knowledge in a blog. As I said, I'm also a consultant, helping people fix their performance problems. I've written a self-published, very successful book about database indexing. And Oracle named me a MySQL rockstar for all the things I do for the community. So when we start a new project or our project seems to be really great and going off, we always ask ourselves, is our stack good enough? Is PHP good enough? Is our framework good enough? Or do we have to use something else which is much more performant? But the point is, this doesn't matter. PHP is fast enough. Even something slow like Ruby or Python is fast enough. Because the problem is not your application server or whether your loop takes a nanosecond longer or is faster. The problem is always in the database. You always hit some roadblocks there and not whether some tiny thing in your language is slow or not. So I know database talks are boring. So from now on, I'm switching into a story mode. We're talking about an invented startup which built an e-commerce solution like Shopify, where anyone can register a shop and sell some goods. So this company built a product that was really great. It's going off. Customers loved it, told other people about it. Money is going in, which is awesome. And with more and more customers, there had been more problems. When they made shopping events, the site was slow. Last Black Friday, the system even failed, which is not great because customers are not happy they didn't sell anything. So that's when you ask your peers, other colleagues, and so on, what can they suggest to solve these problems? And that's when you get mostly non-helpful answers. But it's not a problem of the people you are asking. The problem is that not every application is the same. They are all completely different. Even if someone would build the same application like you, they made tiny differences, so the usage of a database is different. And even if it would be the same application, maybe they have different customers. They are using the product a little bit different. So you can't compare yourself to others. And that's what I don't like mostly about database companies. They tell you they have the golden solution for anything and completely hide all the drawbacks something has, which we will look more at it now. So scaling a database is hard, and you should postpone it for as long as possible. So obviously, you should optimize your application first with the normal steps. Find and fix all slow queries. And I know this is hard, because those query plans you can get are not easy to understand. But there are tools for basically almost any database to help you with that. Like this is MySQL Explain, a free service I developed, which will take the complex plan and show you a graphical output. So you can easily see, great, we read all the rows from the bookings table and apply a filter. So only 213 rows are left. Maybe we should have added an index. Easy as that. After that, sure, we are adding indexing, and I know indexing is hard. It's probably one of the hardest problems because cache invalidation is a fucking beast. That's not easy to tame. And there will be another talk tomorrow by Rob. He will talk more about that, so I would definitely say go there and then look this. And if you solve these two issues, the next thing you always should do is use a bigger database server. You can give it a terabyte of memory, 100 cores, that's no problem. Some people will say it's just throwing money at a problem, but that's not really true. If your company is making millions a year, why should you use a crappy database just costing you $3,000 a year? And a bigger database is so much easier to handle than a fleet of database servers. So scale up as long as you can. Obviously, this didn't work for this startup. One database server was not good enough more. This database server costed too much, so they had to use multiple servers. So the first thing they found was something we as developers really like, which is an approach called multi-master replication. We just have two database servers that are perfectly synchronized, and we can just read and write from both of them. So in our application, we just choose one database server by random for our connection. We are sending a write queries there. The server is applying the change, and then sending the information, what is changed on the disk, to the other primary server, which is also applying the change. And when it's done that, it's sending back, hey, I'm finished. And the server we sent the data to gets the info and only now sends us back the information that this query has finished. So when our query succeeds from our PHP point, the data is already on both servers. That's great because we are getting a guarantee named read after write. We can just write to the left server and read directly after that from the, we write to the left server and directly read from the right server after that, which is really simple for your application to do. But did it solve the performance problems? Yeah, kind of. Like as we can see, we have now two servers and we can do twice the amount of select queries we expected. But somehow performance dropped for our write queries. That's something we didn't have in mind, and honestly, again, this is something database companies don't tell you. So what happened here? Again, take a shopping system and we have now two different requests coming in from two different people, and they're completely independent. And our two PHP processes just select one of the servers by random and send the information, hey, decrease the available tickets for the API platform conference by 1. So both queries are sent independently to the primary servers. They apply the change. Maybe it was the last ticket, so they decrease tickets from 1 to 0 and sends information that there are now 0 tickets left to the other server, which will then apply the change. But when it's trying to apply the change, it's seeing, wait a second, my local value is already at 0. That doesn't make any sense. I have a conflict here. And so it's aborting the change and sending this back to the client, and you're getting the typical messages, hey, query failed because of a conflict. And that's why our write rate decreased. And as I said before, and I will repeat this many more times, not every application is the same. This approach here failed because we have an application with many, many writes to do. Your applications are mostly doing reads. So this approach may work for you, and you can stop here in a very simple approach. As this company did a lot of writes and with shopping events on the same data, they had to look for something else because less writes to do is not something they can live with. So they looked further and found read replication, which is basically the approach you will find with every database provider you have in AWS, in Google Cloud, and whatever, where you can add a read replica. It's quite like before, but now you only have one server you're allowed to write to, and the other one, or other ones, you're only allowed to read from. So again, how does it work? Your insert or update or delete query is sent to the primary server, it's applying the change and directly sending you back the information the query finished. And in parallel, it's transmitting the information to the secondary server. Sounds simple? Yeah, but there's a problem again. And I would say about 90 to 98% of the applications out there have exactly the next problem. So again, we have a customer ordering maybe a product from the shop. We are writing the new product into the database. Everything is great. We are getting the response back. The query is finished for our point. Now the customer switches to another site and maybe wants to see his current orders or a list of all the orders they have. And as we can see here, the information about the order we create in the primary database is not yet transmitted to the secondary because everything is transmitted asynchronously. So our request doesn't know that, and as we are just showing things, we are selecting the secondary server. And boom, we are getting a list back of all the orders the customer has without the newest one. And the customer will be pissed. They will call your support, and you have a new bug in your system. And these things are happening very often because you have to plan for these issues. And again, Rob will also talk about this problem again, and you definitely should go there. So in short, how it's solved, most often you're just adding another cache to the system, and you're saying on every write you do to the database that the current IP address, the current user, the current tenant, whatever you use as identification, will read from the primary for the next 30 seconds, 60 seconds, and so on. So you don't have the problem that the data may not be there because the primary server always has all data. And then some people had the idea, hey, why not make this synchronous? We just wait for it. And now here we have just 5 different servers. Maybe they are in different availability zones because someone had the idea, hey, we want it to be online all the time, even if something is failing. And we are now transmitting the change we have synchronously. And as we can see, the latency to send the data there takes a different time because a different data center may be more far away and it's taking more time. And the upper server here, that takes a long time to apply the change because there may be some problems. Maybe the server is overloaded, maybe the disk has issues, or even the HWS EBS volume can have sporadic issues that writes are taking a very long time to succeed. So if we really switch to synchronous replication, we have to wait for all of these servers to apply the change, which means the query to insert a simple order into the system is now taking almost 18 seconds. Which means we brought down our shopping system just because one of our servers is slow. And that's something nobody can do. So again, database people are creative. They had the idea, okay, great, we can tune that. We make it semi-synchronous. We only wait for the majority of the servers to apply it. So we can exclude the slow ones. Great idea. But again, if you choose your database servers by random, you can again have some servers which have the data and some which don't have the data. So you have again consistency issues. It doesn't help you at all. Like the idea is great of synchronous replication, but it doesn't solve any of your problems, even when people told you it will. But it's not useless. There's a great idea in it. You can, for example, say, I reduce the servers, I need this change to always be applied to be just 1. Why 1? You now have a perfect copy on one of your random servers from your main server all the time. So if that server dies, you have one with all the data perfectly synchronized all the time, and you can just switch over to this one and make it the new primary server. You have high availability. You just need a system to switch over which one is the primary and which one are the secondaries. So if you solved all the issues, are you okay with performance again? Yes, you are, because in this example we had 2 servers, we can do twice the amount of selects, and we are back to normal. We can do 100% of writes because we're always writing to a single server. And we can add as many secondary servers as we want to. Like if we add a third one, we can see we can do more selects, but our writes are staying at the same level. And again, not every application is the same. This application here, this doesn't work for them because they have a very high write rate on shopping events. Your applications are again mostly very read-heavy, and you can stop here. Companies like Notion, Figma, Linear, and so on have used this approach until they made millions and millions of dollars each year. And it worked perfectly. And they only had to switch to something else when they had enough money to hire someone very, very competent to help with these issues, what they have to do now. And what these companies did, and this company here did too, is they switched to something like sharding, which is the holy grail of database scaling. The idea is very, very simple. We have our shopping system, and we say we just divide the data by our tenants, which means all the data for our API platform conference store are stored on shard 3. All for selling some kind of blankets on a mummy store are stored on shard 1, and so on and so on. So you can just add more and more servers and just put different customers there. And if one of the servers is overloaded, you just split it and say, okay, I move just a few shards, a few shops from there to a new shard, and I'm finished again. So that's completely infinitely scalable. And if one is overloaded, you just change some shops and you're good to go. So how do you implement that? Most often, again, you're just adding another store, which is nowadays just Valkey. A year ago would have said Redis. And for every request, you're just asking it, hey, on which store is again the API platform conference ticket store? And it will say, that's shard 3. Awesome. So then you configure your main database connection to say, okay, I need the credentials for shard 3, and you're just doing all the queries on shard 3. Very simple approach. It's easy. Yeah, it's not easy as I promised. Because then product management had the idea, hey, we don't want to be a nameless shopping provider. We want to be one of the known brands. We want to be the shop of shops. People should know us. And we want to build a UI where everyone can see all the orders they did through all the shops, which is a normal thing product management may suggest. So where do we store our users and the products a user bought? We have sharded the system by our shops that doesn't fit in there. So how you solve that is you now have a sharded system for your shops, and you have another database server for your users. And what happens? We have a lot of writes into the users database, because for every order we are storing something in the users database, and this one is failing again. Awesome. What do we do? We have another sharded system. And you can see that's getting complicated really fast because now you're creating sharded systems and so on. But it's still manageable. And now product management was, yep, that's great, but we are not finished yet. We want to show on this dashboard not only the bought products, we want to show live product information from the current information we have stored in the shops. So we need to join that. How do you do that? Like we can run the users tables on the users database, but the products are stored in many different shards. We can't just do a join across servers or even to many servers. So that's when you remember that, yeah, I have to implement a join in PHP. I remember there was something like I shouldn't do that because it's not efficient. Yep. But still you have to, because it's the only way to do. Like every time you have cross-shard queries, this approach is really hard. You don't have to do it manually. There are solutions for that. There is for MySQL the software called Vitess, which had been invented by Google for YouTube and is nowadays maintained by PlanetScale for their enterprise plans. And there's Citus data from Citus data for PostgreSQL, which is doing the same. And there are 3 or 4 more different projects being developed right now for Postgres, but they are just pre-alpha, but there will be more in a few years. So these products can do all of that for you. You just run this query and they are intelligent enough to see that some of the tables are sharded and will do all of that logic internally, and you just see one gigantic database, and what has to be done like cross-shard querying is they're doing it by themselves. For the people who self-host stuff, you can self-host these solutions. They are explanations for that. There are Kubernetes configurations, but please don't do that. You will start these systems, they will work awesome for a very long time, and one day they will fail because they are highly complex systems. And when they fail, you need someone very, very experienced with these technologies to fix the issues. And most probably, you don't have this. So if you really want to use sharding with someone doing all of that for you, you have to use one of the hosted solutions by them, but you can't just host it by yourself. So with all of these problems, did it solve our issues? And yes, it did. With every shard we add, we are getting more select queries and more write queries. And if we want to have much more read queries, we can even combine sharding with read replication, in that we add more read replicas into a shard, and we can do a ton of selects for every shard, and the number of writes we can do for a single server. So that's completely scalable until infinitely. Like, YouTube is still running on that approach, and I mean, YouTube is probably bigger than anyone else here in the room, I guess. So I know that all of that sounds complicated, and I'm sorry I simplified as much as I could, but it is complicated, and it should be complicated because it's a very hard thing. You can't just make mistakes with your storage, where you store everything, because these issues are not solvable. If your PHP has some problems with validation, you just drop a new release and it's fixed. But if you made mistakes to your data, that's forever. That's probably something you can't fix. So keep the approach you do as simple as possible. As I said, upscaling a database server is a perfectly valid approach. You can do that very, very long. I know a ton of companies that are still running on a single server with one server as a replica, a single server with just one server as a backup in case the one fails. Works awesome. And once they need more, they're just using read replication. Sharding is something you probably most often don't need. And why do you want to keep it simple? Because scaling is hard. Scaling is so hard that it's always feeling like that. You're evading an issue all the time. And the more complicated your application and your stack is, the harder it is to evade these firebars. I know companies that took months to solve some issues because they had a so complicated stack that product development was completely still because they had to fix some issues in their application stack. So the more simple you do it, the easier it is to solve these issues. And as I still have time, there's a little bonus for today. The things I shared today are awesome. It's infinitely scalable. You can do a lot of stuff with that, but that's only for CRUD-like operations. You can read, update stuff, and so on. The moment you want to do some analytics, like showing a dashboard on how many sales a shop had, with drill-down functionalities by country, by product type, and so on, these systems fail. Why? Because query time increases a lot with the more rows that need to be analyzed. At some point, it's just not working anymore. So what's the problem here? The problem is that every standard database like MySQL, PostgreSQL, SQLite, and so on are storing rows together in chunks. And if you just want to analyze some things and just need 2 columns aggregated, the database needs to load every chunk just to extract the 2 orange columns from a few rows. That's a lot of stuff you need to load from the disk, which is not needed. That's where columnar databases are used, which are splitting the whole database by the columns. So only the columns must be loaded that your query needs. And as it's storing the columns on its own, it can also apply very good compression. Like if you have the same value repeated again and again and again, it's storing it only once. And if you have very common ones, it's storing it only once. and so on. And it can even then apply very intelligent compression because it has, like, if you store strings, like a country name, they are repeated again. So this very often reduces storage size by 90%, which means you now load only the columns you need, and those are 90% smaller. And this way, analytics works again. And why do I say that? As I said, I do a lot of teaching. I'm currently doing a completely free course, again, it's free, on how to make analytics fast, which is using an extension called TimescaleDB for PostgreSQL, where you just run 3 or 4 commands, and after that you can run your analytics queries on it, and they are very fast, and you can even ask it to pre-summarize data that even 100 million rows take just 2 milliseconds to summarize, which is how you solve the last database problem you have, the analytics part. Now you can solve all your application with create update queries, and now you can also solve any analytics problem you have. So that's it for today.